Now that we have learnt about isoparametric elements and integration over isoparametric elements, let us put it all together. What I'm going to show is a small pseudo code that is meant for quadrilateral 2D quadrilateral elements. So for triangles, the procedure is similar, but there are some subtle differences which I'll point out as I go along. So now we are looping over elements, and let's assume that we are in element number E. And first step that we have to do is extract the nodal coordinates xi, yi for element number E, with I going from 1 to the number of nodes in E. These are the number of nodes in E. And again, you have to decide what type of element it is, whether it's a 4-noded quadrilateral or 8-noded quadrilateral. Depending on that, you will have to choose the order of Gauss quadrature, which we call n order. Once you have chosen an order, you go to the table of 1D Gauss quadrature points and sampling points and figure out what are the Wi's and the Ri's, the weights and the sampling points from I, with I going from 1 to n order. So if you do a second order Gauss quadrature as you would do for a Q4 element, then you will have two W's and two R's, which will be minus 1 by root 3 and plus 1 by root 3, and both the W's will be 1. If you go for third order, then you will have some minus something 0 plus something, as the R's and W's will be I think 1/3, 1/3, 1/3. So depending on the order that you choose, you will have a list of W's and the list of sampling points between -1 and 1. Then for 2D, we will do a loop over ij going from 1 to n order to the power 2. For 3D, we will do a loop over ij and maybe another variable k, which goes from n order to the power 3. Let's look at it for in 2D. So we have two loops here, both going from 1 to n order to the power 2, and then we assemble. So we will have for Q4 element, if we know the element type is Q4, we know that we have to do a second order Gauss quadrature. So we know n order is 2, and then we know that there will be 2 to the power 2 Gauss points, that is 4 Gauss points, and for each of these Gauss points we will cycle through 1 and 2. So we will have the Gauss points as integration points as R1 S1, R1 R1, R1 R2, R2 R1, and R2 R2, where R1 for second order is minus 1 by root 3 and R2 is 1 by root 3. For R1 R1, the weight will be W1 W1. For R1 R2, it will be W1 W2. This will be W2 W1, and this will be W2 W2. In case of 2D, in case of second order, n order equal to 2, all these are 1, so these all come out to be 1, and these would be minus 1 by root 3 minus 1 by root 3, and this would be 1 by root 3 1 by root 3. So that is what you set up. R is set up as one of these 4, and S is set up again as one of these 4. So at that point R and S, which is dictated by your value of I and j, you calculate the shape functions. There would be as many shape functions as there are nodes, so it will have, these shape functions will have will go from 1 to n node. Similarly, you calculate the R and S derivatives of the shape functions. Again, there would be 4 of them each. So I have this capital I as the index. Then we go ahead and find the Jacobian, the inverse of the Jacobian, and the determinant of the Jacobian. So once you have this, you can use the transformation relations, chain rule transformation relations involving the inverse of the Jacobian to find the derivatives of the shape function with respect to the global variables x and y. Again, there would be 4 of them, so I have the index I. Once you know this, you can form the B matrix. the C matrix has to be appropriate for the problem that you solve, and then you make up, this is the contribution of the jth integration points, I comma j integration points, to the total elemental stiffness matrix. So whatever the elemental stiffness matrix is, and you have to initialize this to 0 at the beginning, you will have to add this contribution. And remember, the integral is solved as over I and j, wi wj, and b evaluated at ri as j, b transpose c b evaluated at ri as j, times dead j. This is dead j is also evaluated at ri as j. So this is how the integral is converted into a summation. And what you are doing is you are taking one term here and keep adding it to this ke, so that at the end of the loop, when you do end the loop, you get the full integral with the summation back. You do the same thing with the body force, and then finally assemble it into the global stiffness and force and the loop over elements. In this, you may also have FSE, which is the surface force contribution in case the element shares a surface with a surface of the body which has tractions applied on it. That has not been treated in this algorithm, but if it is there, then you will have to plug it in as well. Now, uh, in case of triangular elements, these two steps will be different, because for triangular elements, remember that the weights and sampling points, the number of weights and number of sampling points for a particular order of integration are different. And it is 2n minus 1 and not it is 2 into n order minus 1, not n order to the power 2. So this loop will go say from 1 to 3 in case of second order Gauss quadrature, and not from 1 to 4. So you will have to do these steps differently in case of triangles, but other than that, these three steps actually differently in case of triangles, and other than that, everything remains exactly the same. So this is how a pseudocode would look like, and this is what you will keep calling for every element in your mesh, and keep adding the elemental stiffnesses to the global stiffness in the way that we have learned using the assembly procedure that we have learned. And this is the heart of a finite element program, and uh, it's very general, and this is what gives finite element program its generality and its strength, because this procedure can be done almost automatically. Once you have coded it in properly, it almost works itself out. Okay, so that's all about isoparametric that I wanted to talk about.